Welcome back. In front of us, we have a question that reads, what is the quantity of heat that will be released when 800 grams of iron is cooled from 96 degrees Celsius to 36 degrees Celsius? Specific heat capacity of iron is given as 450 joules per kilogram per Kelvin. Solution: we are asked to find the quantity of heat, that is Q. The mass of iron is 800 grams, that is the same as 0.8 kilograms, that is by dividing the grams by 1000. The initial temperature is 96 degrees Celsius. The final temperature is 36 degrees Celsius. We are given the specific heat capacity as 450 joules per kilogram per Kelvin. So we want to know Q. We know that the formula to find the quantity of heat is equal to mc delta theta. So Q will be equal to mc into theta 1 minus theta 2. Let that not appear confusing. When you are dealing with a cooling process, as mentioned here, the change of temperature will be the initial temperature minus the final temperature. But if at all the object is acquiring heat or heat is supplied to the object, then the change in temperature, which is delta theta, will be equal to theta 2 minus theta 1. So to write that down, for a cooling process, that is when heat is allowed to be removed from the object, delta theta is equal to theta 1 minus theta 2. That is the initial temperature minus the final temperature. But if you are dealing with a heating process, that is when the object is acquiring heat, delta theta will be equal to theta 2 minus theta 1. So what you have to understand for both cases, the difference will be the higher temperature minus the lower temperature. Like in a cooling process, the initial temperature is higher than the final temperature, so it will be theta 1 minus theta 2. In a heating process, because the object is acquiring heat, we expect it to have a higher final temperature than the initial temperature. So in that case, the change in temperature will be theta 2 minus theta 1. That is final temperature minus the initial temperature. I hope that point is clear. So moving on, we say Q is equal to mc theta 1 minus theta 2. So that is going to be, the mass is 0.8 kilograms multiplied by the specific heat capacity is 450 joules per kilogram per Kelvin. Multiply it by the initial temperature is 96 minus the final temperature is 36. So that is 0.8 times 450 times 96 minus 36 is 60. Then we're going to have 0.8 times 450 times 60, and that is 21,600 joules. What is the final temperature attained when ethanol of mass 1.2 kilograms, initially at 35 degrees Celsius, is supplied with 72,900 joules of heat to raise its temperature? Specific heat capacity of ethanol is 2,430 joules per kilogram per Kelvin. Solution: we are asked to find the final temperature, that is theta 2. The mass of ethanol is 1.2 kilograms. The initial temperature theta1 is 35 degrees Celsius. The quantity of heat supplied to ethanol was 72,900 joules. Specific heat capacity is 2,430 joules per kilogram per Kelvin. So we want to know theta 2, that is the final temperature. We can use Q is equal to mc delta theta. And first, let's try to find delta theta. So what is Q? It is 72,900. This is equal to the mass of ethanol is 1.2 times the specific heat capacity is 2,430 times delta theta. So that is 72,900 is equal to 1.2 times 2,430 is 2,916 times delta theta. So that will be 2,916 delta theta. To find delta theta, we will divide both sides by 2,916. So 2,916 will cancel 2,916. 72,900 divided by 2,916 is 25. So this is equal to delta theta. So therefore, delta theta is equal to 25 degrees Celsius. So how do we find the final temperature? We know that it is a heating process because heat is supplied to ethanol, right? So we're going to use delta theta is equal to theta 2 minus theta 1. Delta theta is 25 degrees Celsius. This is equal to theta 2 minus theta 1 is 35 degrees Celsius. So to find theta 2, we'll say 25 degrees Celsius plus 35 degrees Celsius is equal to theta 2. 25 plus 35 is 60. So 60 degrees Celsius is equal to theta 2. Therefore, theta 2 is equal to 60 degrees Celsius. 800 grams of water is heated in order to increase its temperature from 24 degrees Celsius to 86 degrees Celsius in 9 minutes. Calculate the heat supplied to the water per minute. Specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Solution. This question wants us to find the rate of heat transfer. We can know that from analyzing the problem, which states calculate the heat supplied to the water per minute. So the heat supplied to the water per minute means that we need to know the quantity of heat and divide it by time. So that is rate, okay? It is rate of heat transfer. And you should bear in mind that when you have the quantity of heat divided by time, that is also called power. So power is basically the rate of heat transfer. Now, let's collect the data. The mass is 300 grams. That is 0.3 kilograms. The initial temperature is 24 degrees Celsius. The final temperature is 86 degrees Celsius, and the time is 9 minutes. So we can find Q, which is equal to mc delta theta. That is, the quantity of heat is equal to the mass of the substance times the specific heat capacity of the substance times the change in temperature. So Q will be mc into theta 2 minus theta 1. Okay, we are dealing with a heating process because temperature is increased from 24 degrees to 86 degrees Celsius. So going by that, Q is equal to, the mass is 0.3 kilograms times the specific heat capacity is 4,200 times the final temperature is 86 degrees Celsius minus the initial temperature is 24 degrees Celsius. So that is 0.3 times 4,200 times 86 minus 24 is 62. So 0.3 times 4,200 times 62 is 78,120 joules. So if you can remember, Q is also equal to the power times the time. So by dividing both sides by T, you are finding the power. So that is, power is equal to Q divided by T, and this will be the rate of heat transfer, or it will be the heat supplied to the water per minute. Okay, this time it wants the time to be in minute. So what is the quantity of heat? It is 78,120 joules divided by the time is in minutes. Usually, if you are dealing with the SI unit, you have to convert the time to seconds. But since the question wants you to leave your answer in minutes, you just have to leave it like that. The time in the question is 9 minutes, so there is no need to convert it to seconds. So 78,120 divided by 9 is 8,680 joules per minute. Why? Because time is in minute and the quantity of heat is in joules. So that will be joules per minute. A waterfall is 1,680 meters high. Calculate the change in temperature of a quantity of water that falls from the top to the bottom of the waterfall, assuming no heat is lost to the surrounding. Acceleration due to gravity is 10 meters per second squared. Specific heat capacity of water is 4,200 joules per kilogram per Kelvin. So, solution, we have a waterfall, okay? At this point, which is the top, we have some quantity of water that is at a height of 1,680 meters. So we have a distance of 1,680 meters. And when this water is allowed to fall, it will settle at the bottom. So this is basically what a waterfall is. The quantity of water that is at this position is having potential energy. But when it is allowed to fall down, it builds up kinetic energy, and it is that kinetic energy that will be converted to heat energy. So we want to know the change in temperature that is associated with it. The general idea here is that the quantity of water that you have here at the top, Once it begins to fall down and its kinetic energy increases, the kinetic energy will convert to heat energy. So we are assuming that no heat is lost to the surrounding, meaning that the potential energy that the water has initially is all converted to kinetic energy and is all converted to heat energy. That is what we are assuming. So which means that the energy that we have at this level is equal to the quantity of heat. That is to say, the potential energy is equal to the kinetic energy, which is going to be equal to the quantity of heat. So it is this principle that explains why the water at the bottom of a waterfall is having a higher temperature or is warmer than the water at the top. The simple principle is that as the water falls to the bottom, the potential energy is converted to kinetic energy, and that kinetic energy is what is converted to heat energy, so it causes rise in temperature at the bottom of the waterfall. So in the question, we have assumed that there is no heat loss to the surrounding, meaning that the total potential energy that we have is converted to heat energy. So what is the formula for potential energy? It is the mass times the acceleration due to gravity times the height. This is equal to, the formula for the quantity of heat is mc delta theta. So we can say that the mass will cancel out. That is to say, acceleration due to gravity times the height is equal to the specific heat capacity times the change in temperature. So acceleration due to gravity is given as 10 meters per second squared multiplied by the height is 1680 meters. This is equal to the specific heat capacity is 4200 times delta theta. So 10 times 1680 is 16,800. This is equal to 4200 delta theta. To find delta theta, we divide both sides by 4200. So this will cancel this. Therefore, we can say that delta theta is equal to 4 Kelvin, or if you like, you can say 4 degrees Celsius. Remember that the difference in temperature, either you express it in Kelvin or you express it in degrees Celsius, will be the same, basically. And that answers the question. The thermal capacity of a quantity of water is 840 joules per degrees Celsius. Determine the quantity of heat required to raise its temperature from 30 degrees Celsius to 100 degrees Celsius. Solution: the thermal capacity or heat capacity is given as 840 joules per degrees Celsius. The initial temperature is 30 degrees Celsius. The final temperature is 100 degrees Celsius. We want to find the quantity of heat required to raise the temperature. So we're going to use Q is equal to C delta theta. That is, the quantity of heat is equal to the heat capacity times the change in temperature. Okay? Because the mass is not given and the specific heat capacity is also not given, so we cannot use Q is equal to mc delta theta. So moving on, this will be the heat capacity is 840 joules per degrees Celsius, multiply it by the change in temperature will be theta 2 minus theta 1, that is 100 minus 30. So that is 840 multiplied by 70. 840 multiplied by 70 is 58,800 joules. The heat capacity of copper block of volume 125 centimeter cube is 425.6 joules per degrees Celsius. Its temperature drops from 120 degrees Celsius to 20 degrees Celsius. Calculate the quantity of heat lost by the block. Calculate the specific heat capacity of the block. The density of copper is given as 8.96 grams per cm cube. Solution. The volume is given as 125 centimeter cube. We are dealing with copper block. The heat capacity is given as 425.6 joules per degree Celsius. The initial temperature is 120 degrees Celsius. The final temperature is 20 degrees Celsius. We are given that the density of copper is 8.96 grams per cm cube. So the first question asks us to find the quantity of heat lost by the block, that is Q. And the second question wants us to find the specific heat capacity. So the first thing we will try to do is to calculate the mass of the copper block, because we have the density and the volume given to us. If we want, we can convert first to the SI unit. If we want, we can first try to find the mass in grams, then we convert it to kilograms. The choice is ours. So using density is equal to mass all over volume, then by cross multiplying, mass is equal to density times volume. The density is given as 8.96 grams per cm cube, multiplied by the volume is 125 centimeter cube. So centimeter cube will cancel centimeter cube. Then we will have 8.96 times 125. That is 1,120 grams. So if I want to convert that to kilograms, I will divide it by 1,000. So if you divide that by 1,000, you have 1.12 kilograms. So that is the mass in kilograms. Now we will move on to answer the first question, which is the quantity of heat lost by the block. So question 1, to find the quantity of heat, we can use the heat capacity multiplied by the change in temperature. So that is going to be the heat capacity into theta 1 minus theta 2. The reason for that is we are dealing with a cooling process. And if we are dealing with a cooling process, the change in temperature has to be the initial temperature minus the final temperature, okay? Which is the opposite of a heating process. For a heating process, the change in temperature is the final temperature minus the initial temperature. So remember, for both cases, it is the higher temperature minus the lower temperature. So moving on, the heat capacity is 425.6 joules. That is 425.6 multiplied by theta 1 is 120 degrees Celsius minus theta 2 is 20 degrees Celsius. So that is going to be 425.6 multiplied by 100. 425.6 multiplied by 100 is 42,560 joules. Moving on to question 2, it asks us to find the specific heat capacity of the copper block. So we're going to use Q is equal to MC delta theta. That is going to be Q is equal to MC into theta 1 minus theta 2. Okay, so what is the quantity of heat? We have calculated that as 42,560. This is equal to, the mass is 1.12 kilograms times the specific heat capacity, which we don't know, times the initial temperature is 120 degrees minus the final temperature is 20 degrees Celsius. So that will be 42,560 is equal to 1.12 times C times 100. 42,560 is equal to 1.12 times 100 is 112 multiplied by C, that will be 112 C. So to find C, we divide both sides by 112. This will cancel this. So therefore, the specific heat capacity of copper block will be 42,560 divided by 112, which is 380 joules per kilogram per Kelvin. Or if we like, we can say joules per kilogram per degree Celsius. A heater is used to raise the temperature of 5.5 kilograms of water initially at 20 degrees Celsius to 100 degrees Celsius in 4 minutes. What is the power of the heater in kilowatts? Specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Solution: the mass is 5.5 kilograms. The initial temperature is 20 degrees Celsius. The final temperature is 100 degrees Celsius. The time is 4 minutes. Specific heat capacity of water is 4,200 joules per kilogram per Kelvin. We want to find the power. First, I will try to find the quantity of heat. We know that the quantity of heat is equal to MC delta theta. So that will be MC into theta 2 minus theta 1. So what is the mass? The mass is 5.5 kilograms multiplied by specific heat capacity of water is 4,200 multiplied by the final temperature is 100 degrees Celsius minus the initial temperature is 20 degrees Celsius. So that is 5.5 times 4,200 times 80. 5.5 times 4,200 times 80 is 1,848,000 joules. So the formula that has to relate the quantity of heat and power is that the quantity of heat is equal to power multiplied by time. So if I want to find power, I will divide both sides by time. This will cancel this. So that is to say power is equal to the quantity of heat divided by the time. So what is the time given in the question? It is 4 minutes. If I convert it to seconds by multiplying it by 60, that will be 240 seconds. So going by that, we'll say power is equal to Q. What is the quantity of heat? It is 1,848,000 divided by the time is 240 seconds. Okay, Q is measured in joules, time is measured in seconds. So 1,848,000 divided by 240 is 7,700 joules per second, which is the same as watts. So either you say joules per second, it is the same as watts. Okay, 1 joule per second is equal to 1 watts. But the question asks us to express our answer in kilowatts. So I know that 1000 watts is equal to 1 kilowatts. So if that is the case, 7,700 watts should be equal to, let's say, X. So we cross multiply. That will be X times 1000 watts is equal to 7,700 watts times 1 kilowatts. To find X, we will divide both sides by 1000 watts. So this will cancel this. And watts will cancel watts. X will be equal to, so we can say 7,700 times 1, which is 7,700 kilowatts divided by 1000. So X will be equal to 7.7 kilowatts. The heat of 19,740 joules was removed from 500 grams of water initially at 46.2 degrees Celsius. Calculate the final temperature of the water. Specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Solution: the quantity of heat is 19,740 joules. So that was the heat that was removed from 500 grams of water. So the mass of water is 500 grams, which is the same as 0.5 kilograms. The initial temperature is 46.2 degrees Celsius. We are asked to find the final temperature. Specific heat capacity of water is 4,200 joules per kilogram per Kelvin. So we can use Q is equal to MC delta theta, and we find the delta theta first. The quantity of heat is 19,740. This is equal to, the mass is 0.5 kilograms times the specific heat capacity is 4,200 multiplied by delta theta. So 19,740 is equal to 0.5 times 4,200 is 2,100. When that is multiplied by delta theta, we have 2,100 delta theta. So to find delta theta, we will divide both sides by 2,100. That is, this will cancel this. So we can say delta theta is equal to 19,740 divided by 2,100, and that is 9.4 degrees Celsius. So, but we know that delta theta will be equal to theta 1 minus theta 2, because here the process involves loss of heat, because it says 19,740 joules was removed. So if heat is removed from water or from any object, the temperature falls. So we are going to expect a final temperature that is lower than the initial temperature. Okay, so we're going to use theta 1 minus theta 2. So we're going to say delta theta, which is 9.4, is equal to theta 1 is 46.2 minus theta 2. So collecting like terms, we can say 9.4 minus 46.2 is equal to minus theta 2. 9.4 minus 46.2 is minus 36.8. This is equal to minus theta 2. So the negative signs will cancel out. Therefore, theta 2 is equal to 36.8 degrees Celsius. And that is all for today. Thank you very much for watching this video. Please subscribe to the channel, like and share our videos.